Batch, and I will be the moderator for today's webinar on the topic of case studies, customer data from GMP pilot experiences of twin column systems. This is one in a series of more than 10 webinars on multi-column chromatography for applications in the production of protein therapies. Check out our complete series on the YMC Process Technologies YouTube channel. We understand that you have limited time and came here to hear the content, so we'll forego formal introductions of our company until the end of the webinar. Just a few housekeeping notes and we'll commence with the presentation. Today's seminar is approximately 30 minutes long, leaving time after the formal presentation to answer any questions you may have. This presentation will walk through the experience of multiple end users employing GMP scale twin column continuous capture, sequential batch, and MCSGP enabled chromatography systems on actual end user feedstock. Economics as modeled by the end users will also be shown. We invite you to explore our other webinars that cover a wide range of topics and more attributes of the entire two-column YMC chromatography platform. These are 15 to 30-minute presentations by subject matter experts and are available on our YouTube channel. Today's presentation will cover these topics. First, our presenter will do a quick review of each technology for those of you who may not be familiar with them, but it'll only be a quick overview. Then we'll review case studies on the capture step, sequential chromatography, and MCSGP, HPLC peptide purification, as well as oligopurification. Today's presenter is Dr. Kathleen Milbachler, who is an expert in the field of multi-column process chromatography and was instrumental in the development of the twin column systems platform technology at YMC Process Technologies. Kathleen has worked for more than 15 years in the area of process chromatography, including at different levels as senior researcher in the pharmaceutical industry at Bristol Myers Squibb, Eli Lilly, and Pfizer. She also has taught undergraduate courses for chemical and biomedical students at the Department of Chemical, Biological, and Pharmaceutical Engineering at New Jersey Institute of Technology. Dr. Milbachler holds director position at the AICHE's Separation Division and is also a member of the Scientific Committee of the International Symposium on Preparative Chromatography since 2007. Kathleen holds doctoral and master's degrees in chemical engineering and a master's degree in biomedical engineering. Please welcome Dr. Kathleen Milbachler. Kathleen?
Thank you, Gerard, for the nice introduction. And I want to jump in immediately into today's presentation. As Gerard indicated, it is about our twin column technology, and I will present today about testing we have done at customer sites and the results we have obtained with our technology. Again, our platform for the twin column includes a batch system, the Chromatography Cube, which can be used for LPLC and HPLC application, and our scale-up system for low-pressure application, which include CaptureSMB, sequential chromatography, and traditional batch chromatography, which this system can execute. At the end of the presentation, I will also present you some examples of our newest kit on the block, the MCSGP HPLC system at the GMP scale. And we have given, or we will give seminars where we go into the detail how these technologies are working or how these equipment systems are working. Today, the main focus is on the applications done on the systems. However, I would like to give you a brief overview initially on the CaptureSMB step, and then later when I talk about the other application, also so you have an understanding how the technology work. So as I said, the CaptureSMB is utilizing two columns, twin technology, where we are enabling the higher load on the columns by capturing the flow-through material on the second column. In the startup process, the initial load is done on the first column. Then the columns are put into a cycle, repeated cycle, where then the initial load column is going through the wash, elution, and regeneration step, as shown here on the right side, where the other column is continuously loaded. When the column is clean, it is now put on the backside of the column in the loading position, as shown on the bottom. And then the load is continued, so a higher load can be obtained on the column in the loading zone. Then the columns are disconnected again. The product is eluded of the column on the right side in this case, and the column on the left side is continuously loading. This cycle is repeated until the batch is completed, the entire feed batch is completed in case of a fed batch operation, or for a continuous perfusion reaction until the perfusion is done. At the end, there is one last elution step on the last column, and we're calling that the shutdown process. With this simple technology, we can obtain much higher loads to the column, and so increase significantly the productivity and maintaining the high yields which are usually obtained in a capture step. So let me now go directly into the industrial application of this technology, and I want to highlight here the most prominent, which has been published in the literature and presented also in multiple international conferences, the collaboration we have done with BMS in the last 2-3 years. If we are looking at the traditional batch process, a standard operation of the process, their platform process, this process was then scaled up to or transferred to a continuous capture operation. During this development work, a batch was separated in two parts. One was separated on the traditional batch, as shown on the left side, and the other half was then separated using the continuous capture step. And you can see that during this development work, we are applying the same process steps. The only difference is that during the continuous capture, we are able to increase the load to the columns significantly from 10 CVs to 16 CVs. In this way, the resin could be utilized up to 92% compared to 67% in the traditional batch operation, and the buffer needs could be reduced also. You also see that in the continuous capture, the linear velocities were increased from 300 centimeters an hour to 400 centimeters an hour. Looking at the comparison between the initial development work on the cube and then the scale up to the twin system, very similar separation could be obtained when scaled up to the twin, but also when we then scale down back, we have obtained similar separations on both scales. And I just wanted to show you the consistency of the continuous separation based on the peak areas obtained during the separation. In the initial runs, we had 4 repeats, and you can see in each cases there are very good reproducibility of the elution peaks with very small errors in the area of the peaks. And that could be obtained on both scales, on the bench with the cube and with the Twin 100. We have also comparison here. I just want to show you the significant difference between the traditional batch operation, and here is a 30 hours operation with 16 repeated cycles. And you can see during the 30-hour operation, we could still distinguish between the first load in the startup, where we didn't meet exactly the startup conditions, which was good for display here. So you could see the first elution peak on the column 1, then the first peak on column 2, and then with the second cycle, we are immediately into the steady state operation, and after that, there's no distinction between the elution peaks also. Now comparing the results, again, the batch operation was done on a 17-liter column in comparison to the CaptureSMB steps, which used only a total of 1.6 liters of resins. The runs were one batch run, 4 recycle in the first development step, and then the 30-hour operation with 16 cycles. You can see the masses being separated in each of the runs and the operational time, but the most significant is a productivity increase from 8 grams per liter resin per hour to 20 in the initial development step, and then up to 24.6 grams per liter resin per hour. Development work, we also compared the composition of the product to make sure that we have the same separation, and you can see that the HCP values were within the range compared to the traditional batch operation. The DNA was reduced in the same levels. Protein A leaching was in the same limits. High molecular weight also were obtained, and the purity with STS was also in the same level. So comparing the traditional batch platform process to the capture, we obtained the same results using the twins separation. Switching to another customer, and in this case, the titer is slightly lower for the process. The first example was 5 grams. Now we have 1 gram per liter. And we're using in the batch process a 7.8 liter column. You see in the table on the left side the platform process. Each of the step has 250 centimeters an hour linear velocity, except in the loading only 150 centimeters per hour were used. The loading CVs, of course, because of the low concentration, was 40 CVs, and then we transferred this process to the continuous capture step. And again, you can compare the same process steps were implemented, except we could significantly increase the loading. And during the continuous capture, all the process steps were now at 250 centimeters an hour, which increased the productivity of the process. For the continuous capture, we again used only 10 by 10 centimeter columns. So the total column CV was 1.6 liters in the process. And we could increase the loading from 40 CVs to 49 CVs. That caused a resin utilization and a reduction of buffer needs in the process, and a reduction of the process time from initially 9 hours for the injection to 4 hours per cycle. And I have here the values on the next slide comparing the productivity. So we tripled the productivity from 4.2 grams per liter per hour to 13 grams per liter per hour. And we increase the resin utilization, or reversely said, we need only 67% less resin than compared to the batch process, and we could reduce the buffer consumption by 30% in this case with a low titer. If I take now this case of the 1 gram per liter titer and I estimate 100 kilo scale up would need, I could either use an 80 centimeter ID column, which translates to 100 liters of resin, and separate in 10 days the 100 kilograms, or I could use an 45 centimeter ID column or 32 liters of resin, and need for this over 30 days of operation. If I apply now with the same conditions the twin system, I could use the two 45 centimeter columns. That means I could either reduce the operation time by 22 days if I compare to the 45 centimeter columns of the same amount of resin, or I could reduce the resin needs by almost $1 million if I translate this to dollars. But I also list here on the bottom the estimated buffer savings, which is a very large number. It's almost 15,000 liters for the 100 kilos. So this is 15,000 liters of buffers which don't need to be made, 15,000 liters which don't need to have a tank, and 15,000 liters which don't need to be disposed after the purification. So you can see the significant improvements of implying the twin column separation. I have a third example from my customer, and in this case, they're separating 100 liters on our demo system. In the titer is 3 grams per liter. And also there is a comparison run using a 6.3 liter batch operation or the 10 by 10 centimeter twin column system. The binding capacity is improved from 40 grams per liter resin up to 60 grams per liter resins. To purify the 100 liters for the batch needed 2 cycles. For the twin operation, 3 cycles. The processing time was 6 or 9 hours. The buffer was reduced in the twin operation, and the productivity was also improved from 10 to 20 grams per liter. In a prospective scale up to a 2000 liter with 5 grams per liter titer, a run compared would be using on a traditional batch process, 56 liter column, and for the twin operation, only 28 liters. An estimated improvement of the binding capacity would be from 35 grams per liter to 65 grams per liter. And you can see the improvements in the productivity. Again, it's from 20 to 40. And I have another slide where I go into detail. Let me just pull the slide up so it highlights again. So on the demo system, we could reduce the buffer by 50%. We use 75% less protein A. So that is in dollar and cents, $75,000 less for the protein A, and a productivity improvement of a 2-fold. If I look again at the prospective scale up, there is a time saving for the campaign of 40%, a buffer saving of over 600,000 in a yearly production scheme. And there would be per campaign a saving of protein A from over $400,000 for this prospective process. So on these examples, I hope you have seen clearly the improvements when implementing the twin capture and the reduction of the buffer needs for the process. And I hope I could also show you on the examples on multiple molecules, the process transfer from a traditional batch to the twin operation, and they scale up from the cube to the twin on the larger demo skid. I want to shift gears now to another application, and this can be run on our LPLC twin system, and I just have here an overview of the motor functionality of our twin system that we can, besides the CaptureSMB, we can do a buffer inline dilution. We could run traditional batch, but we also could run sequential or orthogonal chromatography. So instead of having on the capture step two identical columns running in the process, here we would have two different chromatographic modes, and they are running connected. So you could imagine that you have a flow-through operation process connected, or a bind and elute flow-through operation, or a flow-through bind and elute connected with each other. And as an addition, I have also run packed beds with adsorbers connected. So this is the opportunities you have in the implementing a sequential or a chromatography on our EcoPrime twin system. And I have one example here I want to share with you, but I want to refer also to our webinar where we go in more in detail how that works. I have one example here, and this is also bind and elute, where HIC column is connected to an ion exchange column. So in case when the flow through happen, the two columns are connected, and the product is bounded to the second column. And you can see this here on in the middle, that when the feed is loaded to the first column, then the two columns are connected. Then there is a chase where the compound is pushed off the first column and everything is bounded to the second, and then the traditional elution steps happen on the second column. And this would be a general profile you can see on your UVs. So the initial is a flow through of the UV detectors of the first column, and then when we're looking at the binding on the elution on the second column. And this is what you can see. And if we compare now the productivity at two different loads, at 100 grams per liter and 200 grams, we can see definitely there is a doubling of the productivity when using the sequential operation by maintaining the high yields in each cases. So there is no changes in the process to be observed in each cases, comparing the traditional batch to the sequential operation with two different loads. So summarizing, we could say if we using the sequential operation, we could increase productivity at least twice, if not more, through the parallel operation. But that means also there is a significant footprint reduction, not only that we have fewer tanks with the combining of the two modes of operation. We have smaller tanks. We have a single skid operating. The skid can be scaled down, and we can use smaller columns if we want to have the same throughput through the system. And one significant point I want to make also is through the combination of the two modes, the residence time of the molecule is reduced. It is operated straight through without any holding points during the modes of operation, the chromatographic steps. My last example, that is the implementation of the MCSGP process, and it's a handful. It is multi-column, countercurrent solvent gradient purification, and this is mainly applied to polishing steps. And I have a few examples, and this example include a wide variety of biological molecules. My last point is the twin MCSGP HPLC application, and the examples are also obtained on the cube. And I want to show you now the results. And just a few words at the beginning. What does it mean, multi-column countercurrent solvent gradient purification? In a traditional batch operation HPLC, we have to make a trade-off between yield and purity. And as shown here on the left side, we do front side cuts which might not meet the purity requirements. Sometimes this front side and back side cuts are recycled manually, but with implementing the MCSGP process, that is done automatically. So we can obtain a very pure cut in the middle of our product and internally recycle the impure fractions while we still could implement a linear gradient, which is usually used in a HPLC application, and everything is automated. So you don't need to collect, test, the whole operation is automated. Again, we have presented in the past or we have webinars where we go in detail how that works. I want to just highlight a few examples to show how this trade-off can be overcome between purity and yield. So one of the initial was a peptide purification, and you can see here the blue signals show the different batch operation where you have either a very low yield, here in this case 20%, to obtain the required purity of 98.5%. Or you could have a high yield, but you're far away from the purity which is needed. So with implementing the MCSGP process, which is shown here in the upper right corner, you could obtain the needed purity plus the yield. So there is significant yield improvement, a productivity increase of a tenfold. While having the high purity. And that means when you run this kind of operation, you can make a choice. You either have more product or you don't need to produce as much in the upstream processes, which could be also implemented for the oligonucleotide manufacturing. So here we are showing you a number of examples, batch operations, and which are shown in these lower operational points, and you can see the trade-off between purity in the upper left corner, high purities or high yield, and low purities in the lower right corner. But with the MCSGP process, we can reach them. We can have high purity and high yield. And comparing then productivity with the yield, it is shown that with the MCSGP, we have high productivity plus high yield. So for the user, that means we can obtain yields up to 95%, purity similar than in the batch, and have productivity. So you either can scale down your operation with smaller batches, tank sizes in the upstream, or you just make more in less time. Let me see what the time is. So maybe I can just highlight quickly a PEG application here. So we try, in this application, we try to isolate an PEG from an very impure feed stream with multiple PEGylated proteins, and it is can shown that in the MCSGP operation we could obtain again high purity plus high yields for the operation, which unfortunately the batch is really under the MCSGP operation. You know, very comparable results can be obtained. Here is a bispecific purification of monoclonal antibodies. And again, in this case, a very diverse feed stream where you can see here the monoclonal antibodies and then the bispecific, and it can be isolated with a high purity in this MCSGP operation. And the increase of the yield is from 37% to 87%. It's a doubling of the yield. Here again, it's an ADC purification, and this is, when you look at the feed composition, a very, I don't want to say dirty stream, but we can get a very pure product out of this, implementing the MCSGP purification. And I just wanted to highlight here one example where we looked at the process development. And in the traditional batch operation, it required an HIC batch process and an ion exchange purification. And with implementing the MCSGP operation, we were able to reach the product qualities with a single HIC step. So that is a reduction in operational step, improving the yield in the HIC step significantly. And if we are looking here at the development work, we could almost cut by half the development work needed, just designing one purification step using MCSGP compared to two batch operations. So it is a reduction by 37% in the development time here. And also comparing one last implementing MCSGP, and you can see with having a step yield during the MCSGP process of 90%, the overall yield of the downstream purification increased from 21% to 32%. So significant improvement. So it's a reduction of either fermentation needs on the upstream, or we have more product on the downstream, and that would then accumulate to a saving per year for over $4 million. Okay, I want to come to an end and just briefly summarize that through our twin column platform, we could show on multiple examples here that it could be shown that productivity can be improved threefold. Buffer savings are significant in each of the mode of operation, either capture or MCSGP or a sequential operation.
Thank you, Kathleen. That was an excellent presentation. This presentation was sponsored by YMC Corporation. Since 1980, YMC has been a leader in chromatography, producing bench and prep scale HPLC and LPLC systems, packing resin and columns. YMC is a global company with manufacturing offices in over 10 countries. Just a reminder that other aspects of this topic are covered in focused webinars on YouTube. So just go to our YouTube channel and search on YMC Process Technologies, and you'll find all of the other webinars on this topic there. Okay, I'd like to bring back Kathleen for some Q&A, and we do have a few questions. We have limited time, but let's get right to it. So the first question, Kathleen, is for the capture information you presented, there was not an indication in the presentation about the upstream. Was it perfusion or fed batch?
It was a mix of perfusion and fed batch. So in some cases, the customer prepared the fed batch, divided it in two parts, so I could run the traditional batch operation and then the continuous operation simultaneously. In other cases, perfusion was running upstream and it was connected to the system. In some cases, perfusion samples were frozen for the testing on the demo system because of timing issues, but that alluded to that titers were low, below 1 grams per liter in some cases. In some cases, it was over 8 grams per liter when we tested the twin system.
Very good. A couple of questions, all related around the number of pilot processes. How many companies have explored these strategies? What is the status on scale up? What are some of the scales of these processes? And then I'll roll one further one into this, which was, what's the duration of most of these studies?
Okay, I have more than 5 companies tested this demo system, almost 10 systems. It's a diverse customer base. There were CMOs included in the demonstration, but also large pharmaceutical companies, smallest pharmaceutical companies. So the broad spectra which you would expect. Usually the demo is 1 month. Initially, our team comes, set up the demo system on site, train the operators in operation. That could be done within a week. And at the end of the demo phase of 1 month, we might come back to initial additional testing. Sometimes if needed or a longer perfusion is run, we go also sometimes longer in the demonstration to ensure that the customer is happy.
And can you comment, how long have these been in commercial operation, not just pilot operation?
Okay, I'm sorry. So we have now systems in clinical manufacturing, and this is since end of last year, they have been going through the commissioning process, the engineering runs, and they are now in clinical manufacturing in one company.
Thank you. I think we have time for one more question, and it is around how long have these systems run in continuous mode? So taking the amount of time it has run continuously.
So initially, when I started up testing the system just in waters, and I went for a very long period of time, over months, to ensure that the technology is okay. But then now going to customers and connecting them to perfusion reactors, we have gone over 25 days, 30 days in operation of the systems with uninterrupted operation.
Very good. Thank you. And out of respect for everyone's time, we are nearing the end of our time. If you want to keep the questions coming, we'll copy them down and answer them in writing to you. Any other information that you would request, please just contact us at info@ymcpt.com. Thank you for all your questions and your participation today. And as a reminder, this is one in a series of webinars. Look for the other ones on the YMC Process Technologies YouTube page. Thank you and have a pleasant day.